The invariant spacetime interval is calculated between two events, 1 and 2, with time and space coordinates and coordinate intervals as shown as delta s squared equals c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. Now spacetime is the four-dimensional space that includes time as the fourth dimension. We have seen how space and time are connected by the Lorentz transformation, in which both space and time coordinates in one frame must be used to find time and space coordinates separately in another frame. It is hard to draw a four-dimensional space on a two-dimensional surface, so the graph just shows time and the x dimension to illustrate spacetime. Consider events 1 and 2 in spacetime. The line joining them can represent an object that moves with constant speed v between the events. This trajectory is called the world line of the object. Now delta s is not similar to the distance between 2 points in space, for example the points in space of the two events. In three-dimensional space, the spatial distance delta r between 2 points is related to the coordinate intervals as shown. However, the spacetime interval subtracts delta r squared from c squared delta t squared rather than being added to it. This quantity, as it is defined, has the property that it is zero for events connected by a light signal. For simplicity, let's consider motion along the x-axis, so that delta y equals 0 and delta z equals 0. So delta x equals c delta t is the distance traveled by a light signal during time interval delta t. Then for events connected by the light signal, we have delta s squared equals c squared delta t squared minus delta x squared, which is equal to 0. For an object or a signal traveling at v less than c, delta s squared is greater than 0. And if it were possible for a signal to travel faster than c, then events connected by that signal would have delta s squared less than 0. Now delta s squared is invariant because its value does not change in different frames. It is invariant under the Lorentz transformation. So we start with the definition for delta s prime squared in the s prime frame, and we apply the Lorentz transformation to the intervals, and after some algebra, we come up with the following result, which shows that delta s prime squared has the same numerical value as delta s squared, so it is invariant. Note that we have previously encountered other quantities that are invariant, namely rest length, rest mass, and proper time in the context of the proper time interval.